Hey there. So I've been distracted the past month or so with what's been going on in the stock market here, but I just wanted to finish up this video. This will be the last video in our free fall problem, the nonlinear case where we break up the system, transform the system from a differential equation or system of differential equations into a bunch of algebraic equations. And rather than just sitting here listening to me yammer, let's just get right to the notebook and get on with it. Okay, so over to the notebook, and let's zoom in here a little bit. This is the notebook for the linear problem which we've already done, where we've taken the system of equations, we've solved it with the usual Python ODE solver. Then we did some other approximations where we changed the differential equation into a system of algebraic equations. And since these equations are linear, we have a system of linear equations. So we solved this system via two ways. First, we looped through them to come up with a solution, and we got the same thing as above. And then the second thing we did was realize that we could rewrite this in terms of sparse matrices, which is shown here. So this problem just amounts to finding the inverse of a sparse matrix, and once you do that, you can multiply through, and we get the same solutions here. So now for the nonlinear problem. So I've copied the problem statement over to another notebook here, and let's get at it. So I've already done some of the imports here that we are going to need. We're going to need the NumPy thing. We're going to need the solve IVP problems. We're going to also do it with the regular differential equation solver. We're going to need the Matlab, of course, and we're going to need some things from SciPy. And namely the sparse diags command, the fsolve command from the optimization package. And because there are going to be some issues with this, I want to also import some time functions. So let's run that code. Now our system of equations can be passed to the ODE solver, and we've already done that in a previous video. So this is the system of equations. So I'm just going to run this block of code. That's done, and now we could set up the differential equation solver and run that. So, and then we plot that, and here, this is what we get here. So we get a decrease. It takes roughly, what is this, 300 some seconds to hit the ground, say 370 or something. Oh, I have it printed out here. 381 seconds to hit the ground, and this is what the velocity profile looks like. So we basically accelerate very fast, and then we kind of slow down as we begin to hit denser and denser atmosphere, and eventually it doesn't happen in this problem, but eventually we'd plateau to some sort of critical velocity. So for the loop portion, it's essentially going to be the same as before. We're going to discretize each of the derivatives, the first derivative and the second derivative. So our acceleration here, dv dt, is equal to this. I hope I copied this all correctly, so I'll double check it before actually uploading the notebook to GitHub. But our discretization step is here. So obviously the spatial part is the same as before. There's no nonlinear terms in the spatial part. But for the velocity, we have this. Oops, and I did make a mistake here. I didn't add in the other term, so let me do that off of the recording. Okay, so I think I have finally fixed it here. So this acceleration is our gravity term here, and then the drag term here. And I've also fixed that down here and added in the indices here. So again, this is just a loop, and these are the equations we're going to get for the spatial points and then for the velocity points. So let's actually just code up a loop now. So I'm just going to steal from the linear code all of our setup code here. So we're going to create a time vector. G needs to be modified, but we'll keep the 9.8, and now we'll get rid of it. Let's just comment it out for now. And then we're just basically creating placeholder variables for our time, velocity, and position, and we're setting the initial position to 0. Or the initial position to 32,000, the initial velocity to 0. So let's see if that runs and comes in okay. Okay, good. Let us move on and code up the actual loop. So let's cheat again and come up here and see how long we want to take for our time step. So let's go to 382 seconds here. So we're going to say that while our time is less than 382 seconds, we're going to do our loop. While t is less than or equal to 382, I will just copy and paste in some of the constants we need here. So we need the mass, R0 and h for calculating the drag forces. So let's also add in the gravitational part and the drag coefficient part here. Okay, and if you have been paying attention, you may have noticed the date has jumped forward by the better part of a month. I usually record these in 1 day, perhaps 2 days total, but yeah, it's been a very strange month, so I have been neglecting this. So back to it. The only thing I made a change off of the recording, and that was to include somewhere in here. Where was it? Oh yeah, I changed the. I was mixing up lowercase and capital V's, and I also defined a time step here of 0.1 seconds. So I fixed the typos and put that time step in, and we're essentially already here. So what we're going to do now is do t is equal to t plus dt, and we're going to append that to time. So time dot append t. So that should do it. So if we actually run this, it's not catching the time step. Why not? Oh, it's because I had not run the previous cells in the sheet. So now we're good to go. And if I run it now, it just runs fine. So let's just plot these results and see what it looks like. So plt.plot time, and we called the spatial variable y. So let's plot that. So this looks the same as, where is it? Up here. And now let's plot the velocity. So let's let's create a figure here. plt.figure, plt.plot time comma capital V. And we run that, and we get this velocity thing. So we reach a maximum velocity of about 200. Let's see what our velocity up here was. About the same. So this looks identical. So we are good. So this is the Euler method using a loop. Okay, so the last part of this, if you would recall the previous video we did on this topic, we were able to cast the equations of motion, our approximation for the derivatives, the velocity and position derivatives, so the acceleration and the velocity, as a matrix equation, where one matrix basically calculated the derivatives and related the velocity to the position. That's this matrix here, times a matrix of a column vector of our unknown, so our position at every time step, at our velocity at every time step, and this was equal to a column vector over here. We could do a similar thing. Well, I should note here that because this is a linear system, all you need to do to solve this is to find the inverse of this matrix. The issue for the nonlinear system, notice that here all of these accelerations are just a constant 9.8. If we go back to go back here and we look at our acceleration, here it is. It's a nonlinear system and it relates different positions and velocities. So finding the inverse of that matrix would not do us any good, since we could not pull apart, all of our unknowns are not on one side of the equation. However, what we can do is basically rewrite this equation with these accelerations, with those nonlinear terms substituted in for those acceleration. Let me say that again. We can rewrite this equation with our nonlinear acceleration substituted in here for these constants. And we can use a nonlinear equation solver to solve that system. I'm I'm not going to write out this matrix equation right now on that other notebook, just because it's not going to fit on the screen, but I will put it in the final version. But let's just rewrite that system. Let's rewrite it as a matrix in the code, and then we'll pass it into a nonlinear solver and see what we get. So let's go back here and down here. So I'm going to create a function called f, which is going to take in our vector of unknowns, which is the lowercase x. We're going to pass into it our matrix, which we'll call s, and n, which is the number of elements in our unknown vector. And I'm going to put in our constants that we need here. That's just the mass of the skydiver, and the constants we need for the change in gravity and change in air friction. So moving on here. So we can create, we'll initialize an empty vector for our positions, and we'll set the initial value, the 0th element equal to our initial position, which is 32,000 meters. Moving on. And now our accelerations here. Notice that this is the nonlinear acceleration from above, so it's not just a constant anymore, not just 9.8. It's much more involved than that. So now we need to set the initial velocity, so the nth element of that vector is equal to 0, our initial speed. And the last thing we need to do is calculate our residual vector, which is just the product of our matrix S times our x vector minus our y. So that should be equal to 0, and we need to return that. So return res, which is our residual vector. Let's run it to make sure there are no typos. So far so good. We'll see when we actually try to run the code what happens. So let's set up our time vector here, and we'll do that as before by cheating a little bit and realizing that we've already kind of solved the problem here, so we know how long it'll take. So I'm just going to set the time vector here. I want to get the number of elements from the shape of that array. We're going to need the time step delta. So delta is equal to np.diff_t, and we're going to grab the first element of that. So there we go. We also need to set up a vector of our initial guesses for a solution, and we'll call that vector x, and we're just going to set that equal to a vector of all ones. So it's going to be np.ones, and it's going to be twice the number of elements in our time vector, since we have to do both position and velocity. So there's an entry for every time step. There's a position and velocity enter. So that's why we have that factor of 2. So let's run that. That looks good. And now let's actually build that square matrix that we've seen over here. So let's go back to this tab, and I will just steal the code from the linear case here and build our vectors this way. So this D is the diagonal line, this dm1 is the diagonal below that, and then this is that the diagonal that's way off of the main, and that one below it. It's the one that relates the position to the velocities. And just as before, we build our sparse matrix like this, and we get a matrix S. We reset a couple of the elements to make it work. Let me just run that to make sure it came in okay. Looks good. Now we're ready to solve the problem. So what I'm going to do is do start is equal to time dot time, and end is equal to time dot time. And you're going to see a problem here. So I'm going to enter in the code to call this function, and then we're going to run it, and then look at how long it took to run that. Look at how long it took to run that function. And before we even do that, let's come down here and say print time is equal to end minus start. And let's just see if this runs okay. Syntax error. What is the issue? Oh, we need a comma here, don't we? Now what? I believe I pulled in the module time, the function time already, so I don't need to the module name. So let's run that. Still no. Okay, I just reran the whole sheet and it ran fine. So I must not have pulled in the. I must have restarted the sheet without pulling in all the imports. So this works. So now let's call the fsolve function. So y is equal to np. Actually, it's not np. It's just fsolve. Our function is f. Our initial vector is x, and we're going to pass in args is equal to s and n. I believe that's enough. Let's look at this function to make sure they're in the right order. X, S, N looks good. Cool. Let's actually run it and see what happens. So, okay, I am going to edit this down because you can see this is taking a while. And we're done. And you can see what the problem is here. This works out to like 40 something minutes just to solve it, and I haven't even checked to see if it is correct. So let's just plot it out and see what the results are. So let's plot out the spatial part. Problem. So here we're going to have an issue. Oh, actually, okay, we don't have an issue. That looks good. Let's plot out the velocity now. So let's come down here and do plt dot. Let's do plt.figure just to have a new figure. plt.figure, plt.plot, t, and our y vector is going to go from n to the n, and that should do it. Oh, what's the issue here? Invalid syntax. Oh. So position and the velocity looks good, and we get the same kind of maximum velocity. But the problem is this time. It takes like 40 something minutes to do it. And granted, I was watching videos on another tab while this was going on, but still, I mean, the shortest time I've gotten on a problem like this is like 20 minutes. And the issue with that actually is Python's implementation of this algorithm itself. The problem is the underlying Fortran algorithm cannot handle sparse Jacobian matrices, and you can think of the Jacobian as the derivative of a matrix for the purpose of this. And the whole issue, the whole point here is when we were looking at this matrix here, it's sparse, and the corresponding Jacobian matrix is also sparse, but the underlying code for the fsolve routine cannot handle sparse Jacobian, so it's calculating this entire matrix itself with all the zeros. And remember, this is a huge matrix, not this truncated version I've shown here. So this is what's causing our issues. So let's switch back to here. Actually, let's switch over to Matlab, which can handle sparse matrices, and just run it and see what happens. Okay, so I have reproduced this code over here in Matlab. So let me open that. What did I call it? So here it is. This is just the same code that we had before. So let me actually just run this. So run, and we're done here. And I've edited out edited down the time here. So it took like 104 seconds. So a little over a minute and a half. Velocity looks good. There's a plot of that. Position also looks good. So this is a lot quicker than the equivalent in Python, and that's just due to the ability to handle sparse Jacobian matrices. I think I will call it quits here, and in my spare time what I might do is play around and see if I can come up with a way around this issue in Python, or even in Matlab. This 100 plus seconds is not really an acceptable duration of time for this type of thing. So I'll play around with it and see what I can do to speed it up a bit. But yeah, I'm just going to call it quits here. And until next time, see ya.